A quick overview of the Sister Rabbits behind the scenes. Okay, so in the config slide, I will say that for Sister Rabbits, this is somewhat atypical from a standard project because this is relatively CS heavy, so a lot of the code you're going to see is going to actually be related to the problem, versus in most cases, I think that most of the code's actually going to be animation focused. Nevertheless, I think this does highlight some cool things you can do. Okay, so for helper, utilities, config, all that sort of stuff, we have the tree class or tree functor. This is going to be very, very useful. This is at the heart of our scene. So when we're designing this, we definitely want to put a lot of attention to make sure that this is well designed. And what well designed means in Monochrome is that, for one, we're taking in the right parameters, we're representing the input in a way that's easy for us to visualize. So an adjacency list in this respect, we're having the app position. App position is going to be where the root is. And the other thing that we want is that the tags of the interior are thought in a clever manner such that any possible query we would want to make, we can do so easily. In particular, what we have is that if we look at this tree, the thing that I really care about are the thing that's really going to move around are the rabbits. So I want to make the rabbit tag as simple as possible so that's easy to reference. I'm still going to tag the edges. I'm still going to tag the nodes. So the nodes is this black region. The sister is actually the inner circle. I'm still going to tag the edges and nodes so that whenever we do a tag transform, that's going to work out. But those are going to be longer tags so that it still works out, but they're going to be longer tags since I'm not going to have to reference them as much. Versus with the sisters, I'm going to have to reference them a good amount of times, so I want that tag to be as accessible as possible. Okay, in terms of actually defining the tree, it might look a bit complex, but it's pretty simple. We just have a helper function for the node, and then we have a helper function for the tree. This helper function for the tree, all it does is it creates a node for the current value, then creates all of the subtrees, arranges the subtrees, arranges the node with the subtrees, and then adds in edges. The way that we're able to add in edges is that because we have tags, I can identify where all of the heads of my children's subtrees are, and therefore I can add in the edges very easily. Okay, let's look at swap. So swap is what we just do over here. This is going to be a common pattern, and I think this is a very good example, is that notice that before the swap and after the swap, we're in a well-defined tree, right? This looks like a valid tree, this looks like a valid tree. But in the middle of the swap, this isn't a valid tree. This isn't a valid tree because we have sisters all over the place. Like we're in a messed up state. So what happens in monocurl is that if we want to have things like this, we're going to start from a well-defined state. During the animation, we have a transient state, and then we're going to end in a well-defined state. So what I mean by well-defined state is we have type information. What I mean by transient state is we lose type information. So whenever you do something like such as transfer subset or lerp subset or mesh select, typically that's going to have to elide the type information. I won't get into the reasons for that, but you can think about that. If I only select a portion of a car, for example, I can't really call it a car, so therefore monocurl will have to elide type information. All right, that might have been more details than you need, but the key idea is that we're going to start off in a well-defined state. We'll do some, during the animation, we'll be in a transient state, but at the end, we'll be in a well-defined state again, and we want to be in a well-defined state at the end. That's the goal. Okay, so let's see how we actually do this. What I'm going to do is the swap's going to take in the graph or the tree, and it's going to transfer, let's go back a second. It's going to transfer this guy to an auxiliary variable, and this red node this red rabbit to an auxiliary variable, and then it'll animate the red rabbit, it'll animate the blue rabbit to its destination, and then once we're done, we can just go to the final state. Okay, so let's see how that looks in practice. We'll transfer what we need to, and that's very easy because of the way we tagged. Then we'll transform both of these into their target states, and then we're done with the auxiliary variables. Let's set them to nothing, and then let's set the graph to be in its final state, which is well defined. And we know it's well defined because we basically copied the original and made the changes we needed. All right, one thing I do also want to point out is that it would be somewhat wrong to just transfer. If I just transferred from aux A, aux B into the graph, visually this would look correct, but it would lead to errors down the line because as a result of this operation, the graph it's still in, its type information has been lost. Whereas if I did it like this, then we're restoring the type information. That might seem a bit nuanced, and if you want, you can just take my word for it. But at some point, especially when you're doing more and more stuff, you should get comfortable with understanding why that's important. All right. Then I have a bunch of functions related to actually getting the solution. These are just helpful functions related to the graph. I won't go over them too much since it's not really related to animation, so I don't think it's that interesting. And then we have a solve function that's just going to solve the graph by doing a successive series of swaps. And notice that solve and swap, they're progressors, right? So that's another use case of progressors that actually modifies the input variable. Okay, the intro slide isn't too complex. I'll grim over it. One thing I'll notice is that standard library doesn't provide an underlying feature, but we can make our own very easily. Okay, let's look at metacapsules. So metacapsules is what we have over here. And again, it's very easy because with my helper functions that calculate the nodes and the partners, I can identify for every given node what its partner is. And if I know the tag of A and I know the tag of B using this function or using this variable, then I just have to select the tag that corresponds to this and the tag that corresponds to this. And now if I know the position of this guy and the position of this guy, I can easily create the capsule. So this highlights another use case of tags. Okay, and then the other thing I wanted to say is that speaking of tags, we also tag the capsule like this, where we'll take the minimum of the A and B and the maximum of A and B. It's possible that you can just do I comma S, but the reason why that's a bit bad is that if we do a capsule in the other order, we still probably want it to be in the same order. So having this min and max, that's going to be a good way to make sure that the tag's in the order we want. Okay, I'll actually glim over slide 3 as well, just because it's a bunch of state transitions using the functions we talked about. And there's a good amount, but it's actually not that complex. Okay, same thing with slide 4, just a bunch of state transitions. To some degree, slide 5 as well. I do a lot of stuff manually. If you want, you can automate it. But there is some benefit to doing things manually, even if you can automate it, just because I think it reduces some of the cognitive load, and it's very easy to iterate, right? I can easily change this to a different tag. So that's nice. Okay, a bit long, but again, it's mostly just state transitions. Okay, this is just some text. Okay, let's go to slide 8. Okay, in slide 8, we do get a bit more complex. So for one, I have to show the raw graph where I just have the lines. Let's see if we can go to that. Yeah, this guy. And again, this is easy because I can just select the tags. And then we're done. Okay. So in addition to the meta capsule we have over here, I'm going to create this new meta. This new meta, which is going to come from here, but it looks a bit nicer. It's going to also look much nicer in the permutation graph. That's why I created it. All right, transform into, again, this is an animation that's very common, but it has lots and lots of variants. So in this particular instance, I'm going to copy the subset, versus in other instances, maybe you want to transfer the subset. That's the reason why I didn't include it in the standard library, even though it's so useful, because the exact semantics of how you want to do it varies. In our particular case, I'm going to use it for this copy meta function, which is basically going to copy a meta node from the original graph and turn it into a collapsed meta node. That's another thing, is that I do the exact same tags, so this transformation looks nice. Okay, and then we add in all 3, and then to actually collapse it down into a cycle, I basically just hard code the values. We could use trig, we could in fact make this a custom function, but because it was again so simple in my particular case where I only had 3, I might as well just do it by hand, and then we copy the other 2 as well. Okay, then I solve the graph, which is again pretty easy because I already have the function for it, and then we have to do this. A good amount of work, but not too bad, all things considered. Okay, this isn't too bad. Slide 10. Slide 10 is where we use pigeonhole principle to show that the set of the meta node graph is a set of cycles. So for here, I'm first going to have a dot line that's going to help us out, and then we're going to grow the line from 0 to 8, I guess. And then we have a few state transitions. One thing I'll notice is over here where we change the color. This is very easy again because we have the text. Okay, and then I actually transform, I first move that, and then we transform it into this dot circle, but that's easy because we have text. Okay, so slide 11 is where it does get a bit complex. Let me make some notes about things I don't like. I don't really like how randomness is done. I think that's somewhat fundamental just because randomness is at war with functional programming, and it's at war especially with pure functions, and I wanted all functions to be pure. On the other hand, I definitely think randomness could be better. The one thing I really don't like is that I made a really huge mistake where I made the randomness seated on the slide number. But this is a really bad idea because now if I add in a new slide, that's gonna throw away the random seeds for everything in the future. So I'll definitely change that at some point, but for the beta release, we'll just have to live with that. Anyways, let me talk about how this is done. Okay, so for obviously, if we look at this, there's too many colors to do by hand. So what I'm gonna do is I'm just gonna have a few basis colors, and from the basis colors, let me just take in a linear sum. Actually, I guess it's not really a linear sum, I'm just adding 2. But idea is still the same. Let me just take a linear sum, and then we get a wide variety of colors. And I guess realistically, a lot of the colors might not look bad, but I think as a whole, it's a good variety. Okay. I'm not even sure I use this. Okay. Then for sisters, so we have this graph, and the way I'm going to define this, it might be tempting to define this as a permutation graph, and in some sense we kind of are, but you don't want to define it as a pure permutation, because if you define it as a pure permutation, then the swaps are going to be a bit awkward. We have something that's slightly more complex than a permutation graph. So how I'm going to define it is pretty much just based off of the information we have, the sisters and the meta node partners. Okay, so in particular, how I'm going to do this is, let me just say, we can kind of allow our sisters to be arbitrary. So let me just do the natural thing and make 0 a sister of 1, 2 a sister of 3, 4 a sister of 5, and so on and so on. So that's just what I do over here. And then we have to make the partner. So we have that we have 0 and 1 are sisters, but a priori might not be the case that they're partners, right? It might be that 0 is a partner with someone else. Okay, so what we have to do is we have to actually define what's the partner of every single node. And this is what I do over here. And theoretically, we can just make the partner random. Well, not exactly random, but we can make it some sort of random permutation. But that's actually good, and you could maybe make that work, but that's not what I did here, because I think if we did it like that, then it would get a bit awkward. So how I did it is, typically when we have a permutation, we can decompose it into a set of cycles. So we can say 1, 2, 3, 4, and then 4 wraps back to 1, 5, 6, 7, and then 7 wraps back to 5. So this is how I'm defining the set of cycles, 8, 9, 10. So that's how I did it. The reason why this is important, or why this is nice, is that how I'm going to actually display this permutation is based on the partner and sister. Let me just go through the first node, and then let me graph it and its partner. and then let me graph the sister of this first node, and then so on and so on and so on until we loop back, and then we'll go to the next cycle. So you can see how it might be very nice if all of the numbers in a cycle are contiguous, because if there's anything disjoint, we'll kind of have an inversion where A is technically higher than B, but because B was part of an earlier cycle, it'll be drawn before. And that means that when we do this final, is it here? It might be here. No, it's here. When we do this final greedily removing each one, then you could have cases where basically we'll greedily remove it and then they'll get sent over here or something. So it's very natural to have a permutation where all of the cycles are contiguous. It just works out better that way. Again, that's something that you possibly could get away with having it not that way, but this is a very natural idea. I hope you can see that. Okay, anyways, even then we still have a choice, right? I say that 1, 2, 3, and then 3 loops back to 1, but it could just as easily be 1, 2, 3, 4, and 4 loops back to 1. So that's what defines the cycle length, and we just use a random parameter for that. Okay, so now to do the permutation, I guess I don't use the collapse meta. I use another permutation capsule. So I kind of am defining capsule a lot here, but it's pretty simple. Possibly I should have reused them, but I think it's okay to redefine things, especially if they're simple, because the use case is ever so slightly different, so it might work out. Okay, so perm capsule is pretty much just doing all of the stuff the other capsules are doing, but I guess the dimensions are ever so slightly different. Okay, so now for permutation, the way permutation is going to work is that we'll start off with this node. I'll start off with, let's say we're starting off with node 0, and then this would be, let's say this is node 0, and then this is node 1, and then this would be 2 and 3, I believe. I'm not sure, it could be slightly different, but something along those lines. Okay, so we'll graph node 0 and its partner, and then we'll go to the sister of node 0 and its partner. All right, because that's the associated metanode. Okay, and if we go like, I think it's easier to see on a bigger cycle, so we'll go here, and then we'll go here, and then we'll go here, and then here, and here, here, and then we can go through this entire cycle again. It might be the other way around, I'm not exactly sure. Okay, so for actually graphing the cycle, what I'm going to do is see if this node has already been handled in a previous cycle. If it hasn't, then let me just make the count. I need to count the entire thing to know how big to draw it. And then from here, let me just go through the entire thing and place a node at all of the given theta values. Okay, and then we just center it and place them in a line. Alright, so it's definitely very complex, and probably the hardest part is getting the intuition of why we want to have that permutation that way. Having contiguous cycles is a very nice condition. But once you get past that, it does become slightly easier. Okay, so then we just have a permutation and fade. Okay, this permutation swap is going to be really complex. It's probably the most complex animation out of everything here. But I think if we go through it slowly, we should be able to understand it. So I have a permutation swap. It's going to take in a permutation. It's going to take in the two nodes that we want to swap. So we might want to swap this guy and this guy. And then we have a full parameter. This basically shows that over here, I want to draw this purple thing when I'm indicating at the beginning how a permutation works. But at the end, when I'm doing that entire, when I'm just doing this animation where I'm just solving them each one by one, it would be way too redundant. So I just have a Boolean parameter for whether we want to include that purple or not. And then we just have some timing parameters. Okay, so we have A and B. Let's save the original state. That's a common thing to do. Let's save the partners, and let's save the sisters. Okay. Let's go things a bit slower. So now let me calculate where the center of the A node is. Let's go back over here. Okay, so let's say we're swapping these two guys. So let me calculate the center of this guy and center of this guy. Okay, and now as always, let's transfer them to auxiliary variables, and then let's get them to their final state. Okay, and then let's transform. So far it's been pretty similar to the swap on the regular tree. Okay, now we might want to do the purple animation. Okay, so if we want to do the purple animation, let me denote the flash selection. This is basically just says where all I want the purple circles to be. So that's going to be in wherever the two places we swapped, in addition to their sisters. And again, we can just do that with the simple mesh select. Okay, from here, well, this just tells me the nodes that I want to flash, but now I need to convert them to purple circles. So that's just what the map does. So let's write it, let's wait some while, and then let's fade it out. Okay, and we only do that if the full parameter is true. Okay, from here, we are going to transfer the auxiliary variables back into the permutation. Okay, this part is a bit complex. I will admit I don't like it that much, but it does work out. The idea here is I basically just need to, if you don't have this over here, this section, then the tags get slightly messed up. So I wouldn't say this is common, but perhaps a bit more often than I'd like, you do have to do some retags to make it so that the tag transform will look prettier. Let's actually see what it looks like if I don't have this retagged. So if I don't have this retagged, maybe we'll have to go on this one. So if I don't have this retagged, you can see there's this annoying fade animation, which basically has to do with the fact that after we perform the swap, the tags of the capsules get slightly changed. So I'm basically just having some logic to make sure that that fade animation doesn't apply. Okay, but once we're done, I just have to make sure that we set up some invariants, and I'm just going to do that by taking the original one and then just swapping out the partners to get what we want. And then we just do a tag transform, and that's going to do the actual last animation bit. Okay, so that was a lot, but the idea is pretty simple. So we're first just going to actually perform the swap. If we need to, let's highlight the purple region, and then let's actually shift the graph to its new state, making sure that we do some retags to make sure that capsules don't fade in and out. And over here, I'm just doing some examples. So this is the nice thing, right? Is that once I have the foundation, once I have the logistics set up, it's dead simple to this slide and this slide are pretty much just copies of each other, and even this one as well. Okay, the slide 15 is slightly more complex, but not too bad, where I'm basically just solving the permutation graph greedily. There is one thing that I don't like. I kind of realized it a bit too late, but it's not that big of a deal. Basically, yeah. If you saw how sometimes when it solves it, the two sisters swap places, I don't like that too much, and I think if we play around with this, we could solve that. But that is something I don't like. Again, not a huge worry though. Okay, and so we basically just solved the entire thing. There's probably more efficient ways to do this, but if you haven't realized by now, monocurl isn't very efficient. So there's that. Anyways, in parallel with all of this, if I just left this animation where I let it grow out, I solved the permutation graph, it would get far too wide. So in parallel with all of this, I'm gonna zoom out the camera. So this shows that the camera is somewhat useful in a 2D sense as well. Okay. Over here, I'm just creating a random tree. It's actually somewhat important when I'm creating this random tree. It's not going to be... Okay, so this is just creating the colors. Actually, I don't like the colors that much for this one, but whatever. Okay. So when we're actually creating this tree, we can't just create a random tree because most trees... Well, I'm not sure on the exact probability, but I would assume most trees aren't solvable. Yeah, definitely most trees are unsolvable. So we just have to be a bit careful to make sure that we actually do make a solvable tree. And the easiest way to do this is add 2 nodes at a time, where we're basically adding in a meta node every single step. Okay, and then the final one is just a recap. And the only interesting thing here is that we just have pins on every single row so that it doesn't write all at once. So you write this, then this, then this, and this, and then this. Okay. If you have any questions on any of that, I'm happy to discuss. Other than that, thanks for watching.